Okay, so we're talking about saturation. So we have our little red blood cell with our hemoglobin seats here, okay? And at PO2 of 100 millimeters per mercury, we have 98% saturation. So that means that 98% of these are full. Each 98% of these are completely full with 4 oxygens each. Okay, if the amount of stickiness that oxygen has to hemoglobin is a direct result, or is directly affected by the partial pressure. So if the partial pressure of O2 is 40, we're only about 75% saturated. So that means 75% of those hemoglobin seats are full. Okay, so this can be shown here on this graph, and basically this is a graph of the stickiness of oxygen to the hemoglobin. And if we look at this, you can see sort of something interesting. So we've got hemoglobin saturation over here and partial pressure down here. Okay, so at a PO2 of 100, so this is 80, so let's say there's 100 here. So if we look up here at PO2 of 100, we are 98% full. Okay, so we never really get to completely full. Remember, 2% is left floating in the plasma. Okay, but when the plasma is at 100 millimeters per mercury, partial pressure, 98% of the seats are full. Okay, so we said 40. So if we go, so here's 100. If we go all the way down to 40, it's about here. So 75%. Okay. So, 100 to 40, that's a lot, and it hasn't gone down a whole bunch. So even at 40, you still have 75% of these full. So it takes the stickiness is totally dependent or very dependent on the partial pressure, but it's very sticky. So it takes a lot to get it off. But once it does, it does. So here we are at 40, 75%. At 20%, we end up at somewhere here, 35%, something like that. Full. Okay. So this right here, the PO2 of 40 and 75% is basically, your body is basically, kind of at rest. Cells are doing their thing, and using up some of the oxygen, but only a little bit is being used. Only a little bit is being unsticky and going into the tissues. Here at a 20, this is activity. This is exercising, okay, and it's going to cause you to use up and pull more oxygen off of your hemoglobin. All right, so certain things can affect this, right? So this is basically kind of a visual of how sticky that hemoglobin is inside. The oxygens are inside this hemoglobin, how sticky that is. So there are things that can occur in the body that can cause the curve to either go more one side, like towards the right, or move towards the left. So either can become even less sticky or more sticky. So certain things that you do. So if we move it this way, you still get the same curve, but it becomes the as you go down the curve, it takes less to make the oxygen jump off. Okay, it goes down faster. All right, the partial pressures. If we go this way, so this is towards the left, and this is towards the right. So this is going to be less sticky, and you're going to be able to get your oxygen into your tissues much easier. And this one is going to be more sticky. So it's going to be harder to get the oxygen off of the hemoglobin in this instance. So what are some things that can cause this to occur? So if you think of times where you would want this, especially, would be times of exercise. Okay, so exercising will move this curve towards the right. And the reason, so exercise, the reason is that it increases body temperature, and that will push the curve towards the right. It will also decrease the pH. So you get a little more acidic. So when you exercise, you're making carbon dioxide and things that are going to make your body a little more acidic, lactic acid, things like that. Also, along with that, an increase of CO2 will also make the curve go to the right. Okay, and then the last thing is something called BPG, which is, I have to look at the spelling here. So biphosphoglycerate, which I don't even want to even attempt to really spell this, but biphosphoglycerate. And it's really 2,3 biphosphoglycerate. But this is a substance that is created from glycolysis. Comes from glycolysis. And BPG is one of the constituents that come from glycolysis, and your red blood cells only use glycolysis to get energy, to make energy from glucose. Because your red blood cells do not use any of the oxygen that it's carrying. So all of these things bring the increased body temperature, decreased pH, increased CO2, increased BPG, force this curve to the right, making it oxygen less sticky. Okay, so it makes oxygen more available. Okay, and the opposite of this, which would be a decrease in body temperature, an increase in the pH, a decrease in CO2, and a decrease in BPG, would bring it to the left, and that would make it more sticky. So that would make oxygen less available to the tissues. Okay, so I guess that's it. So just understand that, you know, the oxygen loads up on hemoglobin. We're looking at the saturation of it, and when it's 100%, or when it's at 100 millimeter per mercury partial pressure, it is almost 100% saturated. And as it goes down, then it you know, the partial pressure goes down, it changes the shape of the hemoglobins, and that sort of kicks off the oxygen to the area where there's you know, less oxygen. Let's see. Okay, so just make sure you understand basically this curve, okay, this dissociation curve. And what it means to go to the right or to the left, and how that happens. Okay, so we'll talk about this more in class. Please ask questions. I know this is a confusing thing. But yeah, we can clear things up in class on this. All right, so the next thing we need to talk about is how carbon dioxide moves. So we talked about oxygen and how it gets around the body, and we got to know how carbon dioxide gets from the tissues back up to the lungs in order to be breathed out.